Hello, my name is Dewapriya. I am a postdoctoral fellow at Carleton University. Ron Miller is my advisor. Today I am going to present our recent work on the mechanical behavior of nanoscopic multilayers under shock loading. In this presentation, I will show you that the impact response at the nanoscale is significantly different than what we observe at the macro scale. We have heard of many incidents of high velocity impact such as hail damages, bird strikes, meteoroid impacts and shootings. For example, this body armor saved a soldier's life back in 2009. Therefore, it is critically important to develop materials and structures with higher impact resistance. The benefits of conventional protective materials such as ceramics, fabrics and metals have been extensively explored. As we all know, many physical phenomena such as fracture initiate at the atomic scale. For example, if we take a powerful microscope and see inside of a material sample obtained from the nose of this aircraft, we will be able to see atoms where the fracture initiates. With the available computational tools, we can start engineering design at the nanoscale and develop barrier materials with superior impact resistance. Microprojectile impact tests have allowed us to study the impact response of material films thinner than 100 nanometers. Impact tests of multilayer graphene have revealed that their specific penetration energy is significantly higher than that of conventional barrier materials. The specific penetration energy EP is the kinetic energy loss by a projectile during a penetration process divided by the mass of a target material under the projectile, as shown here. Impact tests of ultrathin polymer films have revealed that their EP is significantly higher than that of graphene. This improved ballistic response can be mainly attributed to the lower entanglement density in the near surface region, which leads to a higher plastic deformation of thin polymer films. The experimental results have shown the superior impact resistance of ultra-thin polymer films. At the same time, it has been demonstrated that metallic nanostructures possess superior mechanical properties due to the restricted dislocation movements. Therefore, we can ask, can the multilayer arrangements of nanoscale polymer metal films have a superior impact resistance? MD simulations can help us to answer that question up to a certain extent. So, we use MD simulations to simulate impact test of multilayer polyurea aluminum films. The aluminum films has a grain boundary in the middle and the diameter of the sample is 43 nanometers. Aluminum and polyurea have similar areal densities. I am going to show you a movie of the MD simulated impact test of these two structures. In this structure, aluminum is on the strike face. In this structure, polyurea is on the strike face. Based on these simulations, we can compute EP of these structures. The computed EP or the specific penetration energies of aluminum polyurea multilayers are higher than that of the other nanomaterials. We recently investigated the ballistic performance of multilayer polymer ceramic structures, and I am going to explain to you this work in little bit more details. This is the structure of the polymer used for the study, and this is a typical polymer chain where the contour length is 56 nanometers, and we consider these 5 multilayer arrangements of silicon carbide and polyurea. And this is a typical MD simulation setup where the diameter is 43 nanometers and the projectile is considered as a rigid body, and we use the Vasishta potential to model ceramic and PCFF to model polymer. Vasishta potential has been specifically developed for silicon carbide, and it has been demonstrated that the potential accurately reproduces experimental shock heugony of ceramic. In contrast, PCFF is non-reactive potential and it has not been previously used to study the shock behavior of polyurea, and therefore we need to validate the PCFF before we using it to model shock behavior of polyurea. The other important thing is that PCFF and Vasishta potential are completely independent, and we need to make sure that the interaction between these two materials are modeled properly. In order to validate the potential, we computed the shock heugony of the polymers using the PCFF and compared them with the available experimental data. Experimental results show that cross bonding of polymer chains occur when the shock pressure is approximately 20 gigapascal and the corresponding particle velocity is closer to 3 kilometers per second. PCFF is a non-reactive force field. In other words, PCFF cannot model bond breaking or reformation, and therefore it follows the same path. Based on this investigation, we limited our highest impact speed to 3 kilometers per second. In order to properly model the interaction between the ceramic and the polymer, we conducted density functional theory calculations to evaluate the adhesion between the two materials. We computed the energy change as we changed the separation distance between the ceramic and the polymer. And these are the DFT model we use for the calculation, and S is the separation distance. The energy change with the separation obtained from DFT calculation is given in this figure in black. The energy separation curves obtained from an existing MD force field is shown in red, and the adhesive strength given by that force field is about twice the strength given by DFT. We appropriately modified that existing force field so that it reasonably agrees with DFT as shown in figure C. We observed that the adhesive strength has a significant influence on the energy dissipation mechanisms of nanoscopic multilayers. Now we have a good model to investigate the impact resistance of nanoscopic multilayers, but we need some parameters to compare their performance with the other materials. We can compute specific penetration energy, which is the energy absorbed during penetration, and the ballistic limit velocity, which is the velocity of a projectile when the probability of complete penetration is 50%. It is commonly referred to as V50. Here I am going to explain to you how we computed V50 of this ceramic target using MD simulation. We conducted 4 impact tests on identical targets with impact velocities ranging from 650 meters per second to 800 meters per second. This movie shows the 4 impact tests, where in this case impact velocity is 650 meters per second. We can see the projectile bounces back at this velocity. Now impact velocity is 700 meters per second, now 750. When the impact velocity is 800 meters per second, the projectile completely penetrates the target. Now we can plot the impact velocity versus residual velocity. When the impact velocity is 650 meters per second, the projectile bounces back, so the residual velocity is negative. When the impact velocity is 800 meters per second, the projectile completely penetrates the target, so the residual velocity is positive. We define the impact velocity when the residual velocity is 0 as the V50 of the target. We repeated the same exercise for all 10 targets and computed V50s. This is the S1P1 target and the corresponding curve is shown in red. The term S1 refers to the smallest ceramic layer and the term P1 refers to the smallest polymer layer. When we rotate this target by 180 degrees, or in other words, when we have polymer layer on the strike face, that target is named as P1S1 and the corresponding curve is shown in blue here, P1S1. So, we use the same name convention for the other targets as well. Here V50s are plotted against the mass ratio, which is the mass of the target in the area directly underneath the projectile divided by the mass of the projectile. V50s of aluminum polyurea multilayers are also shown. One interesting observation is that having a polymer layer on the strike face is more effective than having it on the back face, which contradict the macroscopic experimental observations. That can be due to different energy absorbing mechanisms at the two scales. Viscoelastic and plastic deformations of polymer layer on the back face absorb more energies at the macro scale, but we observe that the propagating shock wave generates spore-like failure in the polymer layer at the back face. In contrast, the failure of the polymer layer on the strike face is more like shear plugging and it effectively distributes the shock loading to the underneath ceramic layer. Here we compare the V50s of nanoscopic multilayers with macroscopic barrier materials such as Kevlar, and the nanoscopic multilayers have significantly higher V50s. Moreover, we use the analytical model developed by Phoenix and Corval to predict the V50s of nanoscopic multilayers. We found that V50s of isolated silicon carbide film is higher than that of a comparable aluminum film. But interestingly, silicon carbide polyurea and aluminum polyurea have quite similar V50s. The interfacial adhesion between aluminum and polyurea is higher than the adhesion between silicon carbide and polyurea. This higher adhesion between aluminum and polyurea helps their multilayers to perform better. These are the EPs of different nanomaterials measured using microprojectile impact test. Here EPs of aluminum polyurea layers are shown. Here EPs of silicon carbide aluminum layers are shown. We can see that P3S3 target has the highest specific penetration energy, and we can change the specific penetration energies by changing the thickness and the arrangement of individual layers within the target. This observed higher specific penetration energies of the multilayers can be mainly attributed to the dominant surface effect at the nanoscale. For example, the higher mobility of polymer chains near the surface helps the polymer chains to absorb more energy. And also the free surfaces and interfaces of aluminum makes the dislocation movements harder. In this presentation, I mentioned two interesting observations. The first is, in contrast to the macroscopic observations, casting a polymer layer on the strike face is more beneficial at the nanoscale. The second is, the ballistic performance of a target with a given composition can be remarkably improved by optimizing the layer thickness and the arrangement of nanolayers. In conclusion, these results demonstrate that molecular dynamics can be a very powerful tool to study the shock behavior of structural systems at the nanoscale, which will facilitate the bottom-up design of a new barrier materials for extreme engineering applications. Thank you very much for your attention.